Welcome, my name is Terry Soul, and this is Programming Chaos, a channel devoted to fun, interesting programming projects that can help you hone your programming skills. Today's project is particle life, a very cool model of interacting particles and forces that leads to all sorts of interesting structures and behaviors, as you can see here. One of the keys to particle life is that the forces that are applied break some of the fundamental rules of physics. So in particular, when we think of for every force there's an equal and opposite force, we're going to throw that away. And that's what gives us a lot of these cool effects. In terms of the programming, as you can imagine, the basic idea is we have a list of particles and then we calculate the forces between them, and that allows them to move around. In order to do that programming, though, first we've got to understand these strange forces that are applied. So let's begin there. So this is a graph of how the forces are applied in particle life, at least traditionally, and I'm going to do a slightly simpler variation that I think is a little easier to code, as we'll see in a minute. But the basic idea is that the particles come in different types, usually defined by colors. So here I've got a green particle and a red particle, and they have unique forces between them that are defined by these graphs. So I'm going to say this is sort of the primary force here, and then there's a repulsive force. And the way it works is this red particle, for example, is being attracted to the green particle. And if it gets too close, if it crosses this minimum distance, it'll get repulsed. So the red particle will tend to want to be this far away from the green particle. Now, if this was a traditional physics simulation, we're thinking of them as connected by springs, then if the red is being attracted to the green, that spring is pulling equally on the green particle. So they're being pulled together. That's what particle life throws out the window. And instead we have, for green particles, a completely different force. And it could also be attractive, so they could be attracted to each other, but in this example, it could also be repulsive. So here we have the same green particle, but notice that now the force for green as it relates to red is negative, so green is actually going to be repulsed by the red. And this is part of what leads to these interesting behaviors. If we imagine a green and a red particle, the red particle is attracted to the green, but the green wants to run away, and so they continually move through the space. And that's what leads to all of these interesting dynamics. The issue here that I have with this model is the strange shape of the force. So again, we can make up whatever forces we want, but it's pretty rare to see in nature a force whose maximum is at some particular distance, and then it gets weaker in both directions. And it turns out it's also a little tricky to program because you've got to calculate, well, how far away are we from this middle radius? So a slightly simpler version that works just as well is this. We again have a primary force, but instead of having a weird peak in the middle, it's just continuous. In this case, the repulsive force is n times the primary force, where n is some positive integer. 3 tends to work pretty well. And so any particular particle is under the influence of both of these forces, and so we can think of them as being added together. So if we have a very close particle, we have some attractive force, but a bigger negative repulsive force, so the net force is negative. And then the repulsive force decreases until the point where these two are equal, and that'll be 0 force. And now the force starts to increase until we hit this point where the repulsive force is 0, and then the force is entirely determined by the primary force. And so you get a similar curve with a peak in the middle, and this force could also be a repulsive force. And so if this force were repulsive, imagine it's a straight line like this, then we would add those two together and we would get a net force that looks like that. It's always repulsive, and unlike the previous model, it doesn't have that weird 0 force in the middle. So slightly simpler model that we'll do in code. In terms of the coding, we have 3 variables that we need in both models. We need to know what is this force. We need to know this minimum distance, which is the distance where the repulsive force cuts off. And we need to know a radius, that's the maximum distance of our primary force. And then the other thing that's important is all three of those variables are different between each pair of particles based on their type. So what I mean by that is this. A red particle may be attracted to another red particle, so we have a positive force. But a red particle might be repulsed by blue, so we'd have a negative force. And in the example I had originally, for example, red is attracted to green, so there's a positive force, but green is repulsed by red, so there's a negative force. So we'll need a table for all of the different forces between each pair of particles. We'll need another table for the minimum distances, and then we'll need a third table for the radiuses. And notice the minimum distance should be smaller than the radius of that primary force. With that in mind, we can start the programming. Before I start the coding, a little credit where credit is due. The original particle life was presented as clusters by Geoffrey Ventrella, and he based it on some of the theories of a biologist, Lynn Margulis. In terms of the code, some pieces we need to begin with: the number of types of particles. I'll use 6. The color for each type, which I'll do in terms of color steps. So I'm using a color wheel of 360 degrees, so I take 360, divide by the number of types, and that tells me how far to step for each new color. We need the number of particles, and we need our array list to store the particles, which, if you're going to have a bunch of particles, you've got to call them a swarm. Okay, so now let's start defining the particles themselves. So I'll create a particle class, and each particle needs to know its own position and its velocity and its type. And for the position and velocity, I'm going to be using p-vectors. P-vectors are built into processing. Most languages have either a vector class built in or a vector class that you can load from a library. And a vector just stores an x, y, and in some cases a z value as a vector. Now we need a constructor. So I'm going to start my particles at a random location. I'll have the particles start with a 0 velocity, and then the last piece is to assign them a random type. And in order to do this a step at a time, the next thing I usually add for my classes is a display function so that I can make sure that everything is working okay. And the display function is pretty simple. We just fill in with the type times that color step we defined earlier so that we get nice even distributions around the color wheel, and then a circle at the position of the particle. To make them look a little better, I'll put in a no stroke in the beginning of the program, so we can come over here. And so now that we have the particles, I need to create this array list. So there we'll define the array list, and then we need to fill it with particles. And I'll fill it with the number of particles I defined up here. Oh, whoops, can't do that as an add or as an equals. I need to do it as an add. There we go. And now that I have the swarm of particles, I can draw them. So this will go through the swarm one particle at a time and ask each particle to display itself. Nothing very interesting will happen yet, but we should be able to see all of our particles. There we go, lots of particles. And I think I want a black background so they'll show up a little better. There we go. Okay, so now that we're displaying them all, we need to put in the update so that they move around according to these rules of force. So I'll go back to my particles and define an update function. The first thing I'm going to need is a couple of vectors for doing calculations. So I need to know the direction between the current particle, the one that's doing the update, and each of the other particles in the swarm. I need to know the total force of all of the other particles acting on the current particle and what acceleration that force creates. So I'll define those p-vectors to begin with. So there are some of the vectors that I'm going to need. And then I'll also want to keep track of the distance between the current particle and each particle I'm calculating the force for, because remember, the forces are proportional to that distance. And so now from the current particle, the one running the update, I've got to compare it to all of the other particles. So there we go. That will look at all of the other particles in the swarm. And I have to be careful here, because when I'm looking at the current particle and I do this for loop, it's going to go over all of the other particles, including the current one. And I don't want the current particle to calculate the force on itself. That will mess things up badly. So this way I avoid calculating the force of a particle applied to itself. For each of the particles in this for loop, I'm going to recalculate the direction to the other particle. So I want to make sure I start with it as 0. And so that's multiplying by 0 has that effect. Direction, again, is a p vector, which is this built-in type in processing, and it has a bunch of methods that can be applied. One of them is multiplication, and multiplying by 0 zeroes out that vector. So this is a simple way to make sure my direction is 0 when I begin each new loop. So the first thing I do is copy the position of not the current particle, but the one that I'm interested in the force applying to it. I copy that particle's position into my direction, and then I'll subtract this particle's position, and that'll give me the vector between them. One thing to be very careful of here is you have to use the copy function. If you just set direction equal to p's position, you'll end up effectively with 2 pointers pointing to the same place in memory. And as soon as you start changing the direction, and we'll make some modifications to that, you would also end up changing the position. So in this case, I have to be careful to use the copy function. You could also copy the x and the y value from the position individually into the direction, and that would work just as well. And then this is the second part I talked about. So we have the particle that I'm interested in, the particle that the force is being applied from, and by taking the difference between those, I have the vector between them. And then I need to know what the distance is. And so the magnitude method, or mag method, takes the magnitude of that vector, which is the distance, as a float and stores it. So direction is a vector. Direction and magnitude. Distance is just the magnitude. And then I'm going to normalize the direction vector. So it used to be a vector from the particle I'm interested in to the one that's applying the force. And now I'm normalizing it, which makes it just a length 1 vector. So it's a little short vector, but pointing in the right direction. So I have the distance and I have the direction, and now I can start calculating the forces. So first, I'm going to calculate and apply the repulsive force. I'm going to look at the distance and see if it's less than the min distance between the type of the particle that is running the update function and this other particle p. And so for that, I need to look in the table and look up what the min distance is. I haven't created the table yet, but that's okay. And if we're less than that minimum distance, then we apply the repulsive force. So let me go ahead and create the force. So the first thing I do is copy the direction. So this force I'm applying is in the direction of that other particle. And I'm actually going to multiply it in a little bit by a -1 so that it's pointing the other way, which gives me the repulsive force. So here we go. The first thing I do is multiply that normal vector by the amount of force I want to apply, which is based on the type of the two particles. So the type of the particle running the update and the type of the particle that I'm looking at. And then, as I said earlier on, the repulsive force needs to be stronger than the primary force. So the primary force may attract them together. When they get close enough, I want the repulsive force to push them away. It's got to be stronger. I'm using 3 here to make it 3 times as strong. And as I said, I'm putting in the negative to make sure that it's a repulsive force. So that gives me the total force, but remember the force declines with distance. And so now I have to put in that distance factor. There we go. So the idea is I take the distance, which is between 0 and the minimum distance for the repulsive force, and I map that onto the range 1 to 0. I need an extra parenthesis here. So for example, if the particle I'm calculating the force on is half of the minimum distance, then I want to multiply the force by 0.5, and that's what mapping does for me. So if I'm halfway between these two distances, I get a value that's halfway between those two values, or 0.5. Say I'm a quarter of the minimum distance, then I get a quarter of that, which will actually be 0.75. So I'm fairly close to the particle. I get most of the force. So that's how the map function works. The last thing I'm going to do is multiply this by a scaling factor, K, which I haven't defined yet. You can think of that a little bit like a spring constant, although as we said, these aren't real springs. And basically I need it to scale down the forces. So it turns out the forces that we have here are going to be a little too large in the range -1 to 1, and you get very erratic behaviors. And so this will scale it down. I guess I can add that up at the top. And I came up with the number 0.05 from a lot of trial and error. You can try some other values there. Again, this is scaling down the forces so that the particles don't move quite as rapidly. And this is always a tricky balance in doing these sorts of simulations. Bigger forces cause things to move faster and things happen more quickly and tend to be more interesting. But if your forces are too big, you get these really big jumps. So if two particles get very close together, we'll apply the force and suddenly one of the particles might jump way far away. In a sense, scaling down the forces, you can also think of that as scaling down time. We're recalculating the forces at smaller and smaller time steps to get a smoother behavior. So if your behavior is very jumpy, you tend to want to scale down the forces or to use smaller time steps. And then finally, now that we have the force calculated, I will add it to the total force. And it is this total force that I'm going to use to calculate the acceleration. So in the for loop here, I'm going to calculate for this particle the influences of all the other particles around it, and that's going to add up to the total force, which afterwards I'll apply as an acceleration. In fact, maybe I should do that now. I'm going to add the total force to the acceleration. If I wanted to give the particles a mass, and here I'm basically assuming all the particles have a mass of 1, so I ignore it. But we could, if we assigned each particle a mass, we would divide the force by the mass to get the acceleration. And then we add the velocity, the acceleration to the velocity, and we add the velocity to the position. Now, a couple of things we need to do if we want to wrap around the edges of the screen, which is a good idea, we'll need to adjust for that. So if we don't do that wrapping, we might get, as I sort of said earlier, a red and a green particle that are chasing each other, and they'll chase each other off the screen to infinity. So it's nice to put in some wrapping. Fix my spelling. So this will cause the particles to wrap. Basically, the idea is if the position is negative, we're too far to the left, then adding the width will jump us to the other side. And if the value is too large, we've gone off the right side. Taking the modulus will put us back on the left side. So this wraps for us. And then the last thing that's going to work well is to add effectively a little bit of friction. So over time, the particles will gain more and more and more velocity. Again, that example of the red and the green particle chasing each other, they're going to keep accelerating. And so if we add sort of a pseudo friction to slow things down, that's important for getting a nice result. And I'm going to do the friction just by multiplying by a value that's less than 1. So for example, let's go up and define friction along with our K. I'll use a value of 0.85. So at each time step, the particles slow down by 15%. they maintain 85% of their velocity. This is a fairly high friction, but it seems to give good results. Again, feel free to play with it. And so now what we're missing is our distances and forces. So we need to go define those. Okay, so we need our tables for the forces and the distances, and although I'm not using it yet, the radii as well. So there we go, there's the 3 tables that we'll need, and then I'll come down to my setup and create them. So each of these tables, as we saw at the beginning, are going to be the number of types by the number of types so that we get the values between them. So what is the force between a red and a green and a red and a blue, and so forth. And the same thing for the distances and radii. There we go. So that sets up the size of the tables, and now I need to fill them with random values. And I'm going to do that in a separate function. It's not a bad idea to do some of this in separate functions. I could do it as part of setup, but a function gives me a little more flexibility, and I'll show at the end why that's kind of useful. So let's call this set parameters. So I'll just use 2 nested for loops to go through each row and each column in each of these tables, actually, all 3 of them, setting the values. And so I can begin with the forces. So there we go. If I spell forces correctly, that will set all of the forces between -1 and 1. One thing that can be useful here is to make sure you don't have a lot of very small forces around 0. So an alternative that I find works well is to do this a little bit differently. This will work, but this other approach I find works a bit better in terms of getting interesting results. I'm going to set my forces to be randomly between 0.3 and 1. So I don't have those very small, nearly 0 forces. On the other hand, I also don't have any negative ones, so I need to put in an if and make half of these negative. There we go. Now half the time we'll end up with a negative force, but we won't have those very small forces near 0 because I'm going to start with forces of at least 0.3. Now that the forces are done, I can do the minimum distances and the radii. So for the minimum distances, I'm picking a range between 30 and 50. And remember, that is the point at which the repulsive force reaches 0. And again, you can play with this range and think of it in terms of pixels or meters or kilometers, sort of however you want to think about your model. And you might want a different range depending in part on just things like how big is your window. A bigger window size, you might want bigger numbers there. And then the radii is the radius for which that primary force drops to 0. And that should be a lot bigger than the repulsive force. We have a short range repulsive force and a much longer range, what I've been calling primary force, which could be attractive or could be repulsive. And now that we've defined our forces and our minimum distances, we should be able to run this. Let's see, extra parenthesis there. And so there's our particles, and if you watch, nothing is happening. And the reason nothing is happening is I forgot to call my update function. So we're displaying the particles, but we're not updating them. Let's try this. There we go. And so you can see them sort of drifting apart. So that repulsive force should be pushing them apart. And that is not entirely happening, and I realize why. So we're starting to see some of the particle life behaviors, not all of them yet, but some of them. And the reason we're not seeing all of them is I have not put in the primary force yet. I only have what should be the repulsive force. And the reason this isn't working is if we come back over here, I'm multiplying by the forces times -3, but some of my forces are negative, and you may have already figured this out. So really, I want the absolute value of the force to make sure that it's positive, and then I'll multiply it by -3 to make sure it's negative. There are some cool effects though there, so you might want to play around with that version. So notice that now we just have a repulsive force, and they're all evenly spreading out, with a slight issue. and that is along the edges here, you can see some strange behavior. So the repulsive force forces them just to basically evenly distribute themselves. What's happening at the edge is a little strange, and we'll need to fix that. The reason we have this odd behavior here is although the particles wrap around in terms of their motion, they're not wrapping around when they consider the distance. So in particular, if I have a particle here and a particle over here, the distance between them is calculated as almost the full width of the window, when really, if I have a toroidal world, the distance between this particle and this particle is the short distance you get by going off the ends. So let's go ahead and add that while we're at it. So I have to put that in after I've calculated this direction and before I've calculated the magnitude. And this is how it works. So this is just one of the cases. Spell direction correctly there. So the idea is if the x distance between my two particles is more than half the width of the window, that means the shorter way between them is instead of going through the window, it's to wrap around. And the way to get that wrap around is simply to subtract the width, oddly enough. So imagine that they're 80 apart. I have a window size of 100 and they're 80 apart. Then the shorter way to go is 10 off this side and 10 on this side. So the real distance should be negative 20, because if it's a positive 80 from this particle to this particle, the shorter distance is a negative 20 going around the other way. And so if the distance is 80 and I subtract the width of 100, that does give me the negative 20. So subtracting the width works fine. We can do the same thing, but we have to worry about, well, what if we have these particles that are 80 apart but pointing that way? So the distance is negative 80. And so we need another calculation. If the distance is negative 80, it should become positive 20. And that works like this, very similar. If we're less than negative of half the width, then we add in the width to get everything to work out right. And now we just do the same thing for the heights as well. There we go. So let's try this. So you see they're drifting apart and getting evenly distributed because there's just this repulsive force, but we no longer have these strange behaviors along the edge, because this particle, even though, whoop, it just disappeared, this particle, for example, even though the distance over here is long, it's actually looking at the short distance around to figure out those forces. So this is not very interesting yet, but it's nice because it appears to be looking correct. We only have a repulsive force that forces everything to be pretty much evenly distributed. Maybe not perfectly. You'll notice a few particles that are a little closer together, but that's because the minimum distance varies. So some particles are allowed to be a little closer to other ones. And in general, it kind of looks like the green particles are more likely to be close to other green particles because presumably randomly selected, those green on green distances are a little smaller. And I noticed some flickering on my top and bottom. So let's see, did I mess up my height? Yes, I need to subtract the height there. One of the frustrating things about these sorts of models is it's very easy to get them almost correct. They're generally working, but there's one little error in there that is throwing something off, and that's why I'm getting that flickering behavior, because I put in a plus sign here where I needed a minus sign. So let's try that. There we go, that looks better. None of that behavior. So as you program your particle life or any similar model, it's worth spending a lot of time looking at the behavior very closely to make sure it's behaving the way you expect, because subtle errors in the behavior could imply some errors in the code. Now, the only thing we're missing is what I've been referring to as that primary force, and that actually is going to work almost exactly like our repulsive force. So we can go ahead and code it pretty easily. So the basic idea is the same for the repulsive force on the minimum distances, except here we're using the radii. And again, we're looking at the type of the current particle versus the particle we're comparing it to. And the rest of the code is almost identical except for the -3 and the absolute value and what we're mapping here, because we're using the radii to do our mapping. And the ability to use this map function is what makes the primary force that I introduced, that purely linear force, much easier to code. If we were using the odd triangular force, I'd need to put some ifs in there to figure out what side of the triangle I'm on and so forth. This makes it much simpler to do. And so now we've got our primary force added in as well, and we can see how this goes. So there's our particles all moving around, and it takes a little while for them to sort of form up their clumps, but we can start to see some of the typical particle life behaviors emerging. So here we can see yellow particles that look like they're attracted to pink particles that are attracted to green particles, and we get a fairly classic kind of variation of a worm-like shape. Looks like our other particles maybe don't have very interesting behaviors going on. We find some cellular structures forming. And what's interesting is this is all what's referred to as emergent behavior. So the rules don't say anything necessarily about lining up pinks with yellows or greens with pinks. The rules are just these sort of generic forces. But when we apply those forces, we get these interesting emergent behaviors. Good. So it's nice to try different rules. So if I run this again, it takes a little time for the patterns to settle out. But because we've got different random forces and distances, we're likely to see very different kinds of structures emerging. So here, those sort of cellular structures, if you will, consists of red and yellow and green, which is not the same colors we saw before. And we don't have those sort of like worm shapes of colors following each other quite as much. One more thing I'd like to show that I find kind of nice is if we go back to our main code, I have this set parameters function. I can add in a void if a key is pressed. We'll call set parameters again, and this will re-randomize all of my values. So here we have a model. And in this case, we're getting sort of blue and pink cellular structures and also green and teal cellular structures. And a lot of the particles are tending to avoid all of the other particles. Kind of interesting, fun to watch. But now if I press a key, the rules change, and suddenly particles that wanted to be close to each other want to maybe spread apart, and other ones are attracted. And so we get very different structures emerging. And then if I press a key again, it's almost like suddenly an attractive force becomes repulsive, and you get these sort of explosion-like patterns. And then we can press a key again, and we get a different set of rules. A couple of things to keep in mind as you play around with particle life. One, it can take a little while for things to emerge, so you might have to be a little bit patient to see what sort of structures emerge. Another thing that's important is the initial conditions. So there are lots of examples on the web of very cool sort of worm shapes that move along, or pairs of particles that zip around the screen. Often that's because they were set up in those positions initially. Here we have all random initial positions, and so we tend to get a little more randomized shapes. Although some very interesting, blue is clearly strongly attracted to itself, but as soon as something else gets close to it, they start to move away. Right? We get these interesting, over here, a very complex cellular structure. So this sort of illustrates why particle life models are so interesting, because you get all of these strange emergent behaviors from what's really a fairly simple rule set. So hit, in this case, a button, and we get a different rule set, and they all start moving around in different ways. Other things to think about: the scale that you're working on. So I have fairly large particles, and only 1,000 of them so that the simulation will run reasonably quickly here for you to see it. You could make smaller particles and a lot more of them if you were a little patient or had a faster computer, and that would change how things look. You'll also notice that we've got pretty big gaps between the particles that are repelled from each other. That's because of the ranges that I picked here for my minimum distances. Sort of spreads things out quite a bit. If I had smaller values, we'd see sort of a less uniform distribution potentially. So a lot of room to play around with what values you have, but also the starting conditions. So instead of random starting conditions, if you were, say, to line up by color, you would see interesting patterns emerge. Or maybe do it in concentric circles all the way out from the center and see what patterns emerge. So as always for this sort of model, lots and lots of things to play with. If you come up with a particularly interesting rule set, please feel free to add it to the comments below. And one of the things that I'm missing in that regard, which you might want to add, is printing these. So every time you set the parameters, maybe print them, and so that you can save the most interesting ones. And one last variation, here I have 6 types. I could easily change this to be fewer or more, and that can give you a lot of additional variety as well. Okay, so have fun playing with it, and like I say, if you come up with anything really cool, add a comment down below. Thank you.